So I'd like to introduce the first speaker of the session. It's actually it's nice to be here at the 10th anniversary meeting. I finished my PhD in time to attend the kickoff party at the beginning of the Institute in 2003. I remember thinking that was quite a nice event, and wouldn't it be fun to organise one? So it's been nice to have been given this task. Anyway, inference in the era of big data is what we decided we'd have a session on. Big data sounds scary, but I think it's interesting for us to spend a morning thinking about what are the real challenges for science data analysis that we might want to do in the next 10 years. So I'm just going to spend a few minutes basically setting the scene for the rest of the morning, where we have some very good speakers to talk about these various issues in more detail. Okay, so locally, when we think about big data in astronomy, most of us around here at KIPAC think of LSST. So for those of you that haven't been following this story, LSST is a large, short, stubby telescope that will make a 10-year movie of the visible southern sky at reasonably high resolution. It's going to be at a good site in Chile. And interestingly, all the data will be made public eventually, maybe after a 2-year delay, and shorter for people that are involved in the project. And by the time we get to 2021, I'm sort of expecting this to be a giant international collaboration where everybody is part of the project. So that's an interesting opportunity for everybody. Just to give you an idea of what's being planned for the imaging survey, here's a picture of the LSST field of view with the CFHT legacy survey, deep survey, sort of overlaid on that in red. And all of that fits into one of these patches in the southern sky. And so 20,000 square degrees in 6 filters over 10 years with between 3 and 14-day cadence, depending on how you measure it. So it's just going to be monitoring the entire sky for 10 years. So for us, thinking about large data sets, we might go the other way. Instead of looking on the whole sky, go and look at what one of the images might look like. This is an image from the deep part of the legacy survey. And all of this sky patch fits into this little sky cell here. So an enormous amount of imaging data that needs to be processed and then understood. Here's the plan for dealing with the data, taking from the site down to sea level where the alerts will be processed nightly. We're expecting something like 1 million alerts per night, so there's some understanding to do there. After 10 years, the archive built up here at NCSA will be around 100 petabytes of images and 20 petabytes of catalogs. I'm told that the catalog will be too big to sort, which is interesting to think about. And this data store, if you wanted to, you could instead use it to hold a copy of every book ever written in every language currently in use. Okay, so LSST and other projects like SKA and ALMA and others, it's interesting to ask, well, do they actually qualify as big data compared to other things that are going on at the same time? And there's been some discussion of this in the last year. I have sort of two answers to this. One is yes, because it's not just about the volume we should be caring about. We should be worrying about the speed with which we have to approach the data, or the speed with which the data comes to us, but also the complexity of the data set. A small data set might still be a big data problem if you have to understand it in a very complex way. Okay, another reason for why we should think of these projects as big data is because one way of thinking about big data is just data that you have to adapt your approach to. So if you find yourself doing something qualitatively different in how you analyze the data, then it's probably you're having a big data problem. And so I'm sure Sloan was probably big data for the time. Other data sets around astronomy have been big data to the people who had to understand them. And so some of the new techniques that we might have to think about for the big data era include massively parallelizing an analysis you didn't have to parallelize before, working with database queries rather than exporting the data and then analyzing it, doing things in the cloud and so on. Okay, so this is a little bit of a cheat. It's sort of saying we can lower the bar for what big data means, but it's still big data to the people involved. Okay, so we had at least one person from the industry community here earlier, one of the alumni from KIPAC, and he was raising the question, you know, is this really big data compared to the kind of thing Google is doing? And there's something else to say about the difference between science and industry here, which is that business intelligence is primarily about prediction, and we need to know what's going to happen next so that they can provide a suitable advert in most cases. Whereas science is more about understanding the system. To predict something in industry, you may not have to understand the system, but for us, we need to understand it. That's our job. And so these two enterprises might require different types of models and techniques, although I think we'll see some examples of where we can learn from people from the tech industry. Okay, so here's one example of where a big data problem is coming, both in volume and velocity. LSST will, because it's monitoring in time, it will be exploring a wide range of luminosities and timescales. Here's an interesting plot for timescale against absolute magnitude. Here in solid are variable things we know about, and open boxes are variable things that have been predicted, and then there's a large amount of parameter space that hasn't been explored yet. And so one big problem that LSST has is how to make sense of this stream of alerts, a million a night, and what to do with all of those. And so in order to be able to get the most out of these and follow them up, that means we need to be able to classify each event with some accuracy. And so it's going to be interesting to hear about what machine learning can do for us from Josh Bloom later on this morning. Here's a problem that I'm interested in, so finding and using a particular kind of complex object. And so here's a picture of a strong gravitational lens, which we've been using to do cosmology with. They're useful for other things as well, and they appear as complicated objects. You can see here as in a simulated time stream of LSST images, you see a 4-image gravitational lens system changing in appearance. This one isn't in color, but you can imagine that being a colored item too. And so the challenge is to find a few thousand of these in amongst the billions of objects in the catalog. Here's an idea for one part of the analysis, is to ask, well, does the complex object I see, is it well fitted by a plausible lens model? And if it's not, then it can't be a lens, is the logic. And so by analyzing all of the different epoch images at the same time, we can use all of the information present. So simultaneous inference seems to be an important thing to do. And at least this sort of model comparison question is well posed, so we can calculate some principled statistics on which one we should prefer, whether we should accept it into a sample of detections or not. We can think of some similar kind of analysis fitting many images at the same time for weak lensing. Here are galaxies that have been ever so slightly distorted, and there are billions of these to be measured. We can again think of analyzing all the images at the same time in a multi-fit, but it's also interesting to think about how to analyze a huge sample of objects at the same time as well in a hierarchical inference. And we'll hear more of that later from David Hogg. And I think an interesting question here is, where should we draw the line between our principles and our pragmatism? Okay, so hang on. Particle physicists have been dealing with this sort of big data set for longer than we have. And so we have Dominique Boutigny here, who's going to tell us a little bit about things we can learn from the particle physics analysis for LSST. Okay, some tasks benefit from human input. We're all familiar with this. They include diagnosis and treatment of new problems, or initializing nonlinear optimization. That's one that often requires some manual tweaking. Also serendipitous discovery. How many things in astronomy have been discovered by people looking at the data? And so it does often seem, at least to me, that we're limited by human power rather than computer power. And so a good question for us is, well, who is going to do all this work? Because the things I want to do in the next decade are quite difficult and complex. So Stuart Lynn is here to try and answer the question, what can citizen science do for us in the next decade? Okay, here's a quick example of something we're already doing in citizen science. Here's some outputs from an online lens modeling tool that's been made available to a crowd of people. You can see they're doing reasonably well, making lens models that predict arcs. And the key thing about this piece of software is that it has this option here, that you can build from someone else's result. And in fact, we see on the discussion forum that people really are doing this. C_CLD is a retired financial analyst in Paris who's built on a model that I had a go at. And then Elizabeth B., I think, lives in Germany, is very good at marshalling crowds on the talk system at the Zooniverse. So this is a citizen-led but professional advised investigation that you can go follow yourself. And it's interesting to think about the scalability of that sort of analysis. Okay, meanwhile, these were simple models applied to data to try and understand those data. On the other side of the fence, the simulators are making ever more complicated and sophisticated models of the physical systems that we're interested in. So galaxies, we saw a lot of those yesterday, also large-scale structure, star formation on smaller scales. And so as these simulations get more complex, that starts to sound like double trouble, big simulations being compared to big data. And so we're hopefully going to hear a bit from Rita about how far we can go beyond simplistic matching between data and simulations. How can we get the most out of both of these things? And so just to say a little bit about simulations in the LSST world, here's a system that's being used to make simulated LSST images starting from simulated cosmologies with some simulation of how the telescope might work, both in how it's scheduled, but also how the optics work, how the detector works, and also the bit in between, and trying to understand the atmosphere, to try and make simulated data that is as realistic as possible. Now, at the moment, this system is being used to try and understand how the system might behave in the future. But it's interesting to think a little bit about how the use of this tool, this simulation tool, might evolve to become something more like an inference tool in the 2020s. So here's an example of a simulated image for LSST, and you can see more of images like this this afternoon if you join in with Kirk Gilmore and his unconference session on understanding the LSST camera. Okay, so that's all I wanted to say. Here's this picture is supposed to be of a big, scary data set here, and now we're going to hear from our woodcutters for the rest of the morning to hear about possible solutions to these problems.